Okay, so we actually have talked a little bit about these bonds that connect matter when we talked about phase changes. When something is a solid, it has a lot of intermolecular bonds. When something's a liquid, it has a less degree of intermolecular bonds. When something's a gas, it has basically no intermolecular bonds. So we need to revisit that, intermolecular bonds, intermolecular interionic bonds. It's the reason quite frankly, why everything you know is not a gas. If it's not a gas, it's got some degree of this. Okay, so we're really going to look at these intermolecular bonds. They could connect ions together, which would be more like an ionic chemical bond. They could connect ions together. They could connect ions to molecules, like if you dissolve salt in water. Okay, they could connect molecules to other molecules. So the next slide you can already see is one of my favorite animations. Okay, but if I were to kind of look on a very small scale, what is matter doing if it's in its solid state, like I said before, if it's in its solid state, it has the highest degree of intermolecular bonds. And we know if we want to get something from a solid to a liquid, what do? We add heat. And adding heat, we are breaking some of those intermolecular bonds. So these are my particles. Let's choose purple. These are my particles. You know, these could be molecules. And if it's in its solid state, I'll go ahead and I'll make the dot, dot, dots my intermolecular bonds. And actually, that's kind of been my convention. So it has a high degree of intermolecular bonding. Okay. If something is in its gaseous state, one of the things that we hit at the end of Chem 1 was if it's behaving ideally, basically those particles are independent of each other. And they're swishing around, you know, they have a lot of motion, right? That's something in its gaseous state. And its liquid state, it's somewhere kind of in between. So our purple particles, okay, we have some bonding, but not as much as if it was a solid. So I'll kind of do some intermolecular bonds, okay, just to get the idea. So here's my little famous animation, not my famous animation, okay. So we'll kind of think window loop. Oh, another video. This is I love the phrase at the end here. It says invisible gas. Okay, but you get the idea. Kind of saw the dot, dot, dots on the video too, didn't you? The intermolecular bonds between the water particles. So those dot, dot, dots, those intermolecular bonds, those are what can be broken easily through heat. Okay? And so when we say it takes energy to break bonds, those are the bonds we're talking about in this unit of material. It takes energy to break those bonds. The latent heat of fusion, okay? That's the melting. Latent heat of evaporation. Okay, energy required to phase change, break those intermolecular bonds. And we also talked about this, I think, that when those bonds, or any bonds in general, but when those intermolecular bonds are formed, energy is released. This is where I said it seems like it could almost be a little rap ditty or something. Okay, so that's why your clouds up in the upper part of the troposphere, when water goes ahead and forms intermolecular bonds, it goes from a vapor to a liquid. That's why you see milky white clouds. Actually, energy is released, and it's warmer in there. Okay, and actually, it's that warmth that makes it more buoyant, and that's where you can get instability. Okay, instability. So this is where I actually made, geek as I am, made you this slide. And I'm going to add to this slide a little bit. Okay. So there are 6, and they're listed in order of increasing strength. Okay, 6 ways to connect matter. There is the intermolecular intrionic bond between ions. Actually, to me, that's more of a chemical ionic bond. But then switching it up there is, if your pieces of matter are an ion and something that is polar. So honestly, what you're going to see me here in a minute do is where anytime you see dipole on here, that's a polar substance. So ion and a polar substance. Let's see how I do that. Ion connected to something that's polar. Okay. The next one is dipole-dipole. Or excuse me, the next one's hydrogen bonding. I'll put the next two together. Hydrogen bonding and dipole-dipole. We're going to learn more about hydrogen bonding. I'm going to write on that later. But hydrogen bonding is a special type of dipole-dipole. So just next to the dipole, ordinary dipole-dipole one, I would put polar-polar. Okay, so two polar things, they don't have to be the same thing, just two polar molecules. Okay, when they stick together, they're going to be called, the intermolecular bond is going to be called the dipole-dipole intermolecular bond. The next one is induced, or dipole-induced dipole. So I've been using the word polar for dipole. So induced dipole, I'm going to show you how this works, but this is a sort of intermolecular bond that connects something that's polar and something that's nonpolar. So this has to be a mixture. So I'm going to put polar dash nonpolar. And what's the last one going to be? Induced dipole, induced dipole. What do you think? Nonpolar dash nonpolar. Yep. Nonpolar dash nonpolar. Okay. So just think of blobs of molecules that are sticking together. And this is the options of sticking those together. Or in the case of ion, kind of up above. Okay. So it is a big hairy deal, you know. I tend to be kind of dramatic anyway. But in those 6 different ways to connect pieces, if you hone in on things that must be a pure substance, okay, that would be your ion-ion, your dipole-dipole, which is 2 polar things, your induced-dipole, which is 2 nonpolar things. What this is referring to, and actually we're covering this in my intro Gen Chem right now, but do you guys remember clear back last fall when we said that matter can either be a pure substance over here on the left, or it can be a mixture over here on the right. Okay? This is P-U-R-E right there. And if it's pure substance, we said it's either an element or a compound. Okay? So when it's talking about, when we talk about intermolecular bonds in a pure substance, basically that is either a pure substance of an element or pure substance of one particular compound. That's what pure substance here is. Okay, but we are going to talk also about mixtures and how they behave, how particles within a mixture behave. So, dipole-dipole. That's kind of skipping down to kind of the middle one, isn't there? Ordinary dipole-dipole. And I had you put polar dash polar. Now, they don't have to, you can actually have this in a mixture of stuff. But basically, and I'm going to show you some good pictures of this, but you're going to see where you have a molecule that has a net dipole moment, okay, and you're going to see in 2 separate particles the positive ... to the negative of another, and the negative of one ... to the positive of another molecule, okay, opposite poles. So the HCl molecule, okay, clearly, okay, we have a charge separation. The chlorine is partially negative, the hydrogen is partially positive. So just, you're going to have to kind of listen carefully to, this also has a narration. Okay, so that was a pure substance. This is just a still image, basically, of what you just saw. You kind of see the hot ends. The electrons are being shared, but they're not shared equally. The one that's more electronegative, in that case of the HCl, it was the Cl, runs around with a partially negative, and the hydrogen in that case partially positive. They kind of line up this way. Okay. So above ordinary dipole-dipole, you have a sort of special dipole-dipole connection called hydrogen bonding. Okay, so hydrogen bonding is another situation in which you have a molecule, and within that molecule, I'll go ahead and kind of emphasize this. This paragraph down here says somewhere in that molecule, and this is where sometimes students get thrown off, somewhere in that molecule you need to have an oxygen that will be partially negative connected to a hydrogen which will be partially positive, somewhere in that molecule. Either that or nitrogen and hydrogen. Okay, again, the nitrogen will be partially negative, hydrogen partially positive. Your other choice is a fluorine. Okay, partially negative, partially positive. Just somewhere in that molecule. Okay? If that's the case, you can go ahead and have hydrogen bonding, or you will have hydrogen bonding. So water's a good example. Actually, it's got two OH groups, if you want to kind of count that oxygen as independently interacting with those hydrogens. Okay, so water tends to do this. Just looking at two water molecules stuck together, that is a hydrogen bond. It's a special dipole-dipole bond, intermolecular bond. Okay, so I said oxygen, hydrogen, nitrogen and hydrogen, or fluorine and hydrogen. So let's take a look at ammonia, NH3. Okay, the central nitrogen atom partially negative, the hydrogen's partially positive. So if you stick another ammonia molecule next to it, that connection right there is a hydrogen bond. Dipole-dipole bond, special hydrogen bond. And last but not least, just pure HF. Okay. Now, again, you only need one of these little sites on a larger molecule to allow for hydrogen bonding. Some of you are really interested in biological sciences. Okay. This is supposed to be my helix DNA structure. The thing that keeps it kind of wound the way it is are these bonds that are kind of between the segments. Okay. Hydrogen bonds. So if we pick on water again, okay, there's water. Water in its solid phase versus water in its liquid phase, you can compare the two. Of course, the solid is got more intermolecular bonds, the liquid fewer intermolecular bonds. Kind of a close-up. So those dots, because it's an oxygen-hydrogen bond in one molecule, okay, and the oxygen is providing partially negative to be bonded to hydrogen of another molecule, okay, that is hydrogen bonding. And this caption kind of talks about how we kind of get our six-sided snowflakes. Okay, spatially speaking, water is that compound. H2O is just crazy. Where most liquids, I think this is right. Liquids, when you cool it down, you figure it occupies less space, and liquids do that. Okay, but when something about 4 degrees, when water about 4 degrees is transitioning from being a liquid to being a solid, it fluffs out, and that's actually what this is talking about. So it occupies more space in its solid state than it does in its liquid state. So anyway, those are hydrogen bonds. So one of the things we talked about in Gen Chem 1 is this idea that if you why, just when you substitute, instead of sulfur, if you put in selenium, or instead of selenium, you put in tellurium, okay, which is a little bit heavier. Why does it boil at a higher temperature? And actually, you can explain this with increasing size or weight. But the fact that water boils at such a high temperature is an indication, and actually this is one of the themes for Unit 1. The temperature at which something boils at, changes phases from a liquid to a gas, is an indication of those intermolecular bonds. Now if you were to draw and you know, it's pretty easy to draw the Lewis structure of H2S and H2SE and H2TE. You're going to have the same number of valence electrons in your Lewis structure. So you're going to basically have the same structure as H2O. So it's definitely polar. It's bent and all that. But, so you'll have dipole-dipole intermolecular bonds. Okay. Okay, so similarly, this looks at some other substitutions. So the black line is what we just looked at, again, boiling point temperatures. But do you notice the green line is looking at the hydrogen bonding of HF versus substituting out the fluorine? You pick up the chlorine, the bromine, or the iodine, okay? Yeah. And then the hydrogen bonding in NH3, but no hydrogen bonding in PH3 or ASH3 or SBH3. Okay, we're just kind of substituting instead of nitrogen something, the next elements in the same group. Okay. I'm trying to think now, why is methane up there? CH4. Remember what that looks like is a carbon atom with 4 hydrogens? Is there hydrogen bonding there? No. There's actually no hydrogen bonding in any of those others. But I think the reason they're showing you that is if you look under carbon, you'll see sulfur. If you look under sulfur, germanium, under germanium, tin. Okay? So basically substituting out that atom for its kind of analogous element in the next period. So this is an indication of the strength of the intermolecular bonds. They're strong, but they're not invincible. Just breaking those hydrogen bonds that connect the water to make it a solid. So going down after the ordinary dipole, actually you have dipole, induced dipole. Well, let's skip on down to induced dipole, So I don't know if you've been around somebody who's been in labor before, but one of the things they can do with labor is to induce labor, and that's all I think about when I think of this. Okay, basically they get it started. And so that's what's happening when you take a molecule minding its own business. Remember I told you to put nonpolar for this? Molecule minding its own business, it's nonpolar, and basically, kind of whimsical sort of, there's a region that gets a little more electrons. Electron cloud over here a little bit more than the electron cloud over here. Makes it partially negative and partially positive. Okay, so that's an induced dipole. It happens all the time. Okay, sometimes these are called actually dispersion forces or London forces. So when we start to kind of take a bird's eye view of how particles stick together to make these intermolecular bonds that make them either solid, lots of intermolecular bonds, or intermolecular bonds making liquid, or no intermolecular bonds because the matter's in its gaseous state. Okay, we're actually going to see that behind the scenes, a lot of times there are kind of a combination of these going on in the same chunk of matter. Okay, so I mention that because these dispersion forces, remember dispersion is the same thing as induced dipole, okay? Those actually are present in everything. Okay, induced dipole. So let's take a look at this little video. Basically, nonpolar means that the electron cloud was the same, I2 molecule. It doesn't take much to have a little shift, okay? And then you have partially negative, partially positive. And that can go ahead and induce a kind of a distortion in the electron cloud in one of its neighboring I2 molecules. We know something's got to be going on with I2, the molecule. If it's not in its gaseous state, it has to have intermolecular bonds. So what sort of intermolecular bonds are they? Well, they're not dipole-dipole. Okay. So this is showing you kind of the same thing in 3 images, kind of from left to right. Something where the electron cloud is the same, okay? There's a disruption in where the hot spot is, okay? More electrons over there to the right, to the left, makes it partially negative. That makes it electron deficient to the right, partially positive, okay, and there you go. honestly, the reason, oh, I don't know, I'm not going to go there. Let's keep going though. All right, the purple stuff is I2. The orange stuff is liquid Br2. Okay? Now, remember there were 7 diatomic elements, and you do Hofbräu-Nickel to get the 7 diatomic elements. And iodine and bromine are 2 of those 7. The other 5 actually are gases. So the other 5 run around with no intermolecular bonds, if they're behaving ideally. So along with this induced dipole goes this property called polarity, or excuse me, polarizability. Polarity, it kind of goes do it definitely has to do with polarity. But polarizability is your ability to basically get that distortion in the electron cloud. Okay? Polarizability. Your ability to induce a dipole on something that's nonpolar. And again, it happens a lot. And like I said, these last few slides in this part will kind of emphasize that. Some things are more polarizable than other things. And if it's polarizable, then you can go ahead and get that started to partially negative, partially positive, and you go ahead and get the induced dipole connections going on. So with size in general comes easier polarizability. Now, I said that when you substitute out, we looked at the H2O, H2S, H2SE, H2TE. And remember, forget about the H2O because that's got hydrogen bonding, that's really strong. But as you substitute, instead of the sulfur, you put in the selenium. Instead of the selenium, you put in the tellurium. It kept getting, the boiling point temperatures were higher. Well, tellurium is a bigger atom. It's got more electrons. Okay, its polarizability of the H2TE is a lot more than the H2S. Okay. So one of the things that you're going to want to be able to do, and your homework will give you some practice at that, is to be able to identify intermolecular bonds that are going on. And one of the things when you kind of look at relative strength of that stuff sticking together due to intermolecular bonds is you need to look at that stuff's ability to be polarizable if it's nonpolar. Or even if it is polar, because those induced dipole, I'm going to kind of switch and call them dispersion forces. But that last force we talked about, okay, dispersion forces or induced dipole, those are a player in everything. So this is where you may or may not want to do this, but on the sheet I gave you, this is where you might want to kind of take that sheet and basically ignore the ion-ion and ion dipole, and you can kind of do this and call this van der Waals forces. Okay. Yeah. And not our books, but some other books actually, and I wouldn't write this down necessarily, but beware that in some cases they use van der Waals forces to just talk about that last induced dipole. Okay. So one of the things I would do though is down here at this bottom one, the weakest one, where they're nonpolar and you have to induce dipole to get them to stick together, I would write dispersion forces there. It's the synonym. So dispersion forces are those where you induce a dipole. Okay. So we have a couple of simple molecules here. F2 is kind of like I2. Okay, so when you look, I already told you it's a gas. And basically it's not polar because the net dipole moment there in the center is 0. Okay, notice you have the boiling point temperature over there on the right. Now these columns right here, I mentioned dispersion because what is dispersion? Dispersion is induced dipole. So basically the only way you're going to get an only way you get F2 molecules to stick to each other now, we're not talking about that chemical bond between them. In order to get them to stick to each other, you're going to have induced dipole. Okay. The next one, HCl. Definitely chlorine is partially negative, hydrogen partially positive, very much polar. Okay, it's net dipole moment of 1.08. Okay, but notice that, so it definitely has dipole interactions going on, but only like about 20% is dipole-dipole. The other 80% is that induced dipole, even though it's polar. That was my point. Okay, HBr, notice that it's getting heavier. Going down, the halogens, chlorine, bromine is heavier than chlorine. It's got more electrons. It's more polarizable, okay, bromine is, than chlorine. So HBr definitely has even more of those dispersion, even though it's polar. Okay, it has that nonpolar thing going on. Okay, and the last one is going on down to the next halogen. So if you especially look over here at the boiling point temperatures, okay, over here, okay, notice we definitely have a trend in increasing boiling point temperature. Okay, just substituting out the halogens. Okay, so last slide here. This is the blue, the light blue. There's a darker blue coming up, but that's the total. And in this case, the yellow is the induced dipole, or that dispersion forces. So argon is a gas at room temperature, but you can cool it down to go ahead and get it to come out of its gaseousity and add a little bit of pressure, and that's even better. Okay, so you can get argon to liquefy, form intermolecular bonds, but they would be the induced dipole form. Okay, and this kind of, these next two, the HI and the HBr, they kind of go back to, actually we just looked at them on the previous graph. Remember, the blue line is the total forces. The yellow line is that dispersion, or induced dipole, and only with the HBr, only with the bromine instead of the iodine do you start to get a little hint of the blue is the dark blue, that is the polar, or dipole, and this is the dipole-induced dipole. Okay, HCl, definitely polar. Okay. So what is so special about these last two guys? They have hydrogen bonds, exactly. And so actually, remember, hydrogen bonding is just a special form of dipole-dipole. And so that's why the dark blue is so high there. Okay, so you know what's next. Assignment slide. Okay, so I do have a little, you know, I have this little movies, so I got one to give you. So these two will be due on Wednesday. Let's take a look at them. See if this will open up. Check this out. You guys got to see this. This is what I did in my. This is what I did today in Chem 122. You know, we talk about properties, and I played the 20 questions thing, and so I asked them. Kind of that first column is they were. I was thinking of a cheeseburger, and they had to. I went around the room and they had to ask me questions about it, you know, to try to narrow it down to a cheeseburger. And then, was it viscous? You know, I said no. And then they had to say what kind of property that was. I guess it would be kind of viscous, but it's not a liquid. Anyway, that's fun. So let's go on to what you guys need to see. There we go. Okay, so for that first one. So that first one, basically, you have compounds A through E, and you're supposed to, kind of like those last figures, you're supposed to say, in a blob of that, all right, a compound, what sort of intermolecular bonds do you have going on? So I went ahead and kind of backwards you know, you're supposed to say how much hydrogen bonding do we have, how much dipole do we have, just general, okay? And then how much dispersion forces do we have? First off, dispersion forces, what can you say about all those? Do they all have dispersion forces or none of them have dispersion forces? They all have dispersion forces, exactly. But actually for number one, I said it's kind of not too bad to go ahead and pick out if you see an OH, an NH, or an FH. And if there isn't one of those, then it can't be any hydrogen bonding. Does that make sense? What you're doing is basically, oh, and I didn't say this, did I? I should have. I'm going to, at the top, say draw the Lewis structures, because I really think you need to, because you haven't drawn enough of them. I think with the Lewis structures, you're going to see, if it's polar, with the Lewis structures, you're going to see, do I have an OH, do I have conditions necessary for hydrogen bonding? Okay. And then that number 2 there is if after drawing Lewis structure, if you see the molecule is polar, then you're going to have number 2. And that number 2 is that dipole-dipole. Okay? Let's see, what else did I say? What other words of wisdom? Oh, I did say. I guess I did. Let me go ahead and speed this up. Okay, so draw the Lewis structure of the little heart there. Look for hydrogen bonding as the molecule polar. So I'll go ahead and post these. So the next one is kind of fun. And actually, in next week's lab, we will be doing some, this will definitely come into next week's lab. So it's a question about benzene. And benzene, the formula for benzene is 6 carbons and 6 hydrogens. Okay, so I went ahead and showed you the 2 resonance structures of benzene. Okay, remember what a resonance structure is basically swinging lone pair electrons. And in this case, I'm just moving the double bond, those pi electrons. So the benzene is circular, or anyway, it's a ring structure. I was looking at ring. They call that a ring structure. So 6 carbons in a ring. Hydrogen's kind of coming out, spiking out from each carbon. 6 carbons in a ring. Hydrogen's extending out there. Okay. So that's benzene. Yes, thank you. I brought benzene today. Okay. Exactly. So the cool thing about that then is, along those lines, okay, an easier way to draw benzene actually is that 3rd one up there. So we're going to talk later on soon, actually, in Unit 1. We need to kind of talk about shorthand structure of drawing structures. Shorthand structure of drawing structures oftentimes have this sort of stick thing going on. You kind of see right here. And it's assumed that actually at each of these 6 vertices, a hydrogen is extending. We'll kind of talk about that. But that's benzene. My favorite one is this one, where you just draw a circle. And the reason you draw a circle is because those pi electrons are delocalized. That's to say, you know, like if you dislocate your shoulder or something, you kind of, like, and so that basically, they're running around. Benzene is an awesome, reactive, crazy sort of structure. And actually that goes along with this problem. Because in this problem they say, all right, let's consider these sort of situations in which you substitute one of those hydrogens. You pluck off a hydrogen, and in organic chemistry you learn more about how this works, and you stick on something else. So in the first case, we're sticking on a chlorine atom, the next case a bromine atom, and the last case, actually this is called a hydroxyl group, or an OH group, for one of the hydrogens. That's it. So I can draw those structures down there. I lifted from the problem. The problem goes on to say it gives you the boiling point temperatures of all that stuff. So I just kind of diagrammed the problem for you down there. So it gives what the highest boiling point temperature for the case where one of the hydrogens has been knocked off and replaced with an OH. What's so special about that structure? Hydrogen bonding, exactly. Hydrogen bonding. Why, and so that's how you're going to answer your thing, right? What's the deal here? What's the difference between chlorine and bromine? If you look at the periodic table.
Bromine
Bromine's heavier, exactly. So it makes it more, starts with letter P. Polarized. Exactly. Very good. Over here, this is one for you, because on the previous homework, you guys are supposed to say, use the thing polar, okay? So what do you think? Polar or non-polar? Where's the center of partial positiveness? I'd say the center too. Very good. Because the hydrogens are going to be partially positive, carbons are going to be partially positive. Where's the center of partial negativeness? Also in the middle. They annihilate each other. So polar or non-polar? Non-polar. Okay? What about either one of these? They'd be polar. Very good. Yay! What's your secret? Okay, so very good. So these are due Wednesday. See you then. Only tell if you want to tell.